Hey everyone, in this video we're going to learn how to identify transformations of parent functions. More specifically, we'll be given functions in which multiple transformations have occurred. So as a reminder, our transformations are scaling, reflection, and translation. So we may be given a function that has been both scaled and translated, and we have to identify both transformations in the correct order. The best way for us to figure out how to do that is to actually start with a parent function and apply a few transformations to it. Our first example, write the equation of the parent function y equals x squared after a vertical stretch by a factor of 3. So our scale factor is 1, 3. So in our function y equals x squared, we're going to divide y by 3, and then that's equal to x squared. Right, we can divide x by 1, but it wouldn't change the value of x. Now in y equals form, we have y equals 3x squared. As a reminder, when we write equations after transformations, we're always doing the opposite, because the equation is always telling us how to get back to the parent function. So if we're multiplying the y values by 3 to get the graph we're looking for, in the function, we're dividing y by 3 to get back to the parent function. So now write the equation of the scaled function above after a shift left 1 and down 2. Now we're starting with y equals 3x squared, and we're applying a translation. So left 1, we're subtracting 1 from the x values. Down 2, we're subtracting 2 from the y values. In our scaled function then, we're going to add 2 to the y values, y plus 2, and then in parentheses, inside the parent function, we're going to add 1 to x, so we have the quantity x plus 1 squared. Written in y equals form, we have y equals 3 times the quantity x plus 1 squared minus 2. Now the follow-up question here is, what happens if we change the order? So let's do that. Let's switch the order of the transformations. Same parent function, but now we're starting with the translation. So write the equation of the parent function y equals x squared after a shift left 1 and down 2. So same translation of -1, -2. We'll take the parent function, we're going to add 2 to y, and then inside the parent function we're going to add 1 to x. In y equals form, we have y equals x plus 1 squared minus 2. Next, write the equation of the translated function above after a vertical stretch by a factor of 3. So same scale factor of 1, 3. In the translated function, we're going to divide y by 3 times x plus 1 squared minus 2. Right, x divided by 1 is just x, so I did not write it as x over 1. Now we need to multiply both sides of this equation by 3. Now we have to pay particular care because we have this minus 2 here. So I want to think of this in brackets, and we're going to distribute the 3 to each term. So that's going to give us y equals 3 times x plus 1 squared minus 6. And our goal with doing it in the opposite order is to see if the order we apply the transformations in matters. So if we scale then translate, or translate then scale, do we get the same function? Would we get the same graph? And we can see here we have a minus 6, when in the last slide we had a minus 2. So we can see that we in fact do not get the same function. So that means the order that we apply transformations in matters. Now what does that mean for identifying? It means that the order we identify them in also matters. And let's look at that next. So we can see that the order of the transformations are applied to a parent function matters. And when identifying transformations that are being performed on a function, it is easier to look for scaling and reflections first, then look for translations. Now let me be clear here. You can do it in any order. Some I find more difficult than others. I find it easiest to identify those scaling and reflections first, and then follow that up with the translations. And the key to doing that is rewriting the function in a particular way. If we can do that, then we can identify the scaling reflections, followed by the translations, and our life becomes a little bit easier. So I've started with a general parent function, y equals f of x. So first let's apply a scaling of a, b. So we're multiplying x by a, y by b. So in our function, we're going to divide y by b, and we're going to divide x by a. Now we're going to apply the translation. So the translation, if we're adding d, so I had to use c and d, since I already used a and b for the scaling, we're adding d to y. In the equation, we're going to subtract d from y. Now notice y is in the numerator, so that subtraction is going to occur in the numerator as well. So we're going to have y minus d all over b. And then similarly for x, if we're adding c, then I'm going to subtract c from x. X is in the numerator, so I'm going to complete that subtraction in the numerator as well. So I have x minus c all over a. So if we write our function in this form, right, with a fraction on each side, one inside the parent function and one with the y's on the left side, then whatever the denominator is the scale factors on x and on y respectively, and then the subtraction or addition in the numerator tells us our translation. If one of the scale factors is negative, that means we also have a reflection. So I find this the easiest way to deal with a function where multiple transformations are occurring. Now I think the best way to wrap our head around this is to do examples with numbers. So determine the transformations in the correct order occurring to each function in comparison to the parent function. First, we have y equals 4 times the square root of x plus 3. Our parent function here is y equals the square root of x. Now, we want to move everything outside the parent function over, so that's only the 4. So we're going to have y over 4. And then it's just x plus 3. So if I wanted to, I could write this as x plus 3 divided by 1. And for our first example, it may be helpful to think that way. Okay, so first thing we want to look for is our scale factor. So our scale factor is 1, 4. Right, 1 here, 4 there. We're dividing x by 1, y by 4, which means we're really multiplying x by 1 and y by 4. So what does this mean if we wrote it out? We have a vertical stretch by a factor of 3. Okay, and then we're going to follow it up with the translation. So look to the numerators. So we have x plus 3 in the function, which means that we're subtracting 3 from x. And we're not adding or subtracting anything from y, so 0. So what does that mean? That means we're then following it up with a shift left 3. And whoops, vertical stretch by a factor of 4, not 3. Mixed up my numbers there. Glad I caught that. Okay, now let's look at our next example. Y equals the quantity 5x to the third plus 1. Our parent function is y equals x cubed. So first thing we want to do is subtract the 1 from both sides. And while we're at it, let's rewrite the 5x. So I'm going to rewrite that as x divided by 1/5, just like we did in the scaling video. So first thing, and we can make this y minus 1 over 1 if that helps us. So our scale factor is 1/5 1. So what does that tell us? That tells us we have a horizontal compression by a factor of 1/5. And then we're going to follow that up with the translation. Nothing happening to the x's. And in the function, we're subtracting 1 from y. That means we're really adding 1 to y. So that's going to be followed up with a shift up 1. Okay? So the key is rewriting it in this form. If we can do that, that makes identifying the transformations a bit easier. Same directions, our next function is y equals -1 times the absolute value of x minus 6 all divided by 3. So first we'll move the -1 to the other side since it's outside the parent function. So we have y divided by -1 equals the absolute value of x minus 6 all divided by 3. First things first, we want to identify that scale factor. So we're dividing the x's by 3, so we're multiplying x by 3, and dividing y by -1, so we're multiplying by -1. One of our scale factors is negative, so that means we have a reflection as well as a scaling. So written in words, we have a horizontal stretch by a factor of 3. And then we're multiplying y by -1, so if we negate all of our y values, the points would move across the x-axis. So this is a reflection over the x-axis. And then we're following that up with the translation. So the translation here, so we have x minus 6 in the function, so we're adding 6 to x and nothing to y. So we're following that up with a shift right 6. Now, just taking a moment, whether we horizontally stretch it or reflect it first, that won't matter. We can interchange those, okay, because we think of a reflection as a scaling anyway. Okay, but we want to do those first and then identify the translation. Next up, we have y equals 2/3 times the cube root of 2x plus 4 and then minus 7. So now we're getting a bit more involved. We have a lot more going on in this function. So first thing, we want to add 7 to both sides. So we have y plus 7 equals 2/3 times the cube root. And while I'm doing that, I'm also going to factor the 2 out here because I want just x in the numerator. Next, we can divide by 2/3. So we have y plus 7 over 2/3. That equals the cube root of, let's rewrite inside the parent function as x plus 2 divided by 1/2. Now I know, that looks really weird. We would never think to do that on our own. Wouldn't be something that we would try to simplify into. But doing so, what's our scale factor? Well, our scale factor on x is 1/2, on y is 2/3. Makes life easier to identify the scale factor. Okay, so what do we have? 1/2. So we have a horizontal compression by a factor of 1/2. And then 2/3, follow that with a vertical compression by a factor of 2/3. And then we're following that up with a translation. So x plus 2 in the function means we're subtracting 2 from x, and y plus 7 means we're subtracting 7 from y. So we're following that up with a shift left 2 and down 7. So the hardest part really is writing everything out. Hey, looks weird to rewrite the function in that form, but by doing so, we can easily see the scale factor, easily see the translation, and if there's a reflection, that's easy to identify as well. Next up, we have y equals 4/3 times the quantity x divided by 2 minus 1 squared. Okay, so we have a 4/3 outside the parent function, so we can divide y by 4/3. Now the issue is we want one fraction inside the parent function, because then what's in the numerator is the transformation and the denominator is the scale factor. And we don't have that right now. So what we can do is think of this as 2 over 2 with a common denominator. We can rewrite this as x minus 2 over 2 squared. And if we do that, the scale factor, so x is being divided by 2 in the function, so we're multiplying by 2. Y is being divided by 4/3, so multiply by 4/3. So we have a horizontal stretch by a factor of 2, a vertical stretch by a factor of 4/3, and then we're following that up with a translation of, let's see, x minus 2 in the function, so we're adding 2 to x, nothing to y, following that up with a shift right 2. Okay, so all this one took is a little bit of simplification, right? X over 2 minus 1, combine the two terms so that we get one fraction, and then, like we said earlier, the denominator is a scale factor, the numerator will give us our translation. Now we have just a general y equals f of x parent function. So y equals 3 times f of 10 minus 5x. So we'll start by dividing by 3. And inside of the parent function, I want it to be a positive x, so we can factor out a negative 5. And that would give me negative 2 plus x. So we can rewrite this as y divided by 3 equals f of x minus 2 all over negative 1/5. Again, a little weird to write that. If we're multiplying by negative 5, that's the same as dividing by negative 1/5. But in doing so, our scale factor is negative 1/5, 3. So we have a horizontal compression by a factor of 1/5, a vertical stretch by a factor of 3. We're negating the x value, so that's a reflection. And if we're negating x, that's going to reflect it over the y. So a reflection over the y-axis. And then we're going to follow that up with a translation, x minus 2, so we're adding 2 to the x and nothing to the y. So shift right 2. Wow, all right, that was a little tough. We had 4 different transformations going on. Took a bit of writing, but identifying really wasn't that bad. Next, what do we got? Okay, y equals negative 3/5 f of x plus 1 divided by 7 plus 8. All right, so they're throwing more at us. So we'll start by subtracting 8 from both sides. Equals negative 3/5 f of x plus 1 over 7. Then we can divide both sides by negative 3/5 f of x plus 1 over 7. Okay, time to identify. So start with our scale factor. So our scale factor is 7 negative 3/5. So we have a horizontal stretch by a factor of 7. Then we have a vertical compression by a factor of 3/5. We're negating the y value, so that's going to be a reflection over the x-axis. And then we're following it up with a translation. Need more room here. Okay, so what's that translation going to be? Translation of, so x plus 1 in the function, we're subtracting 1 from x, y minus 8, adding 8 to y. So we're following that up with a shift left 1 and up 8. Hi, another involved one, but the work was more in writing out all of the transformations, not actually identifying them. Okay, last question. Describe the effect the transformation g of x equals 1 divided by m times the cube root of x minus n, where m and n are positive integers, has on the graph of the parent function. Okay, so I'm going to put a y instead of g of x. So y equals 1 over m cube root of x minus n. So that's y divided by 1 over m equals the cube root of x minus n. Okay, so we can think of this as x minus n divided by 1. So our scale factor is 1 comma 1 over m. So m is a positive integer, so that might be 1/2, 1/3, 1/4, but it's definitely a fraction that's smaller than 1. So now we have a vertical compression by a factor of 1 over m, whatever that is, we're not sure. And then that's followed up with a translation of n0. So n is positive, means we're going to be moving right n units, right? So a shift right n units, whatever n is. Okay, so that would be our description. A vertical compression by a factor of 1 over m, followed by a shift right of n units. Okay, so there we have transformations on our parent functions. Multiple. Every example had more than one transformation occurring, whether it was a scaling and a translation, maybe a reflection and a translation. Some had a bunch going on. Okay, but the key is rewriting it in that form. If we can get it in that same format each time, then identification becomes that much easier. So practice with a few identification problems before moving into the graphing video. Click the Amazon link down below for my algebra workbook so you can practice on your own. Give the video a like, and before you go, click that subscribe button so you can see more videos just like this. Thanks for watching.